Awesome. So, June, thanks for joining us today. You and I met, I want to say like 3 months ago. Is that more or less correct? Um,
Yeah.
okay. When I was in Boston very briefly for my TA obligations as a PhD student. And Wei said, I've got uh, a friend with similar nerdy interests. We should grab lunch and chat. And we ended up talking about Rust over fried waffles and chicken for like an hour and a half. And then
Yeah.
I roped you into giving a talk to the seminar group. So really happy that you were able to do so. And looking forward to seeing a little bit of what you've been working on.
Oh yeah, super happy to be here. I don't seem to be able to share my screen. Oh,
Oh,
there
I
we
think
go.
that
Okay.
that's fixed now. Yeah.
Okay, perfect. So give me 1 second. Select the right window. Can you all see this?
Yes, nice and clear.
All right. So welcome to my talk. Today I'm going to be talking to you about Untwine. This is my library for pretty simple parsing, and my name is June. Um, Little bit of background about myself. I call myself a parser aestheticist because I'm really an enthusiast, but I want parsers to be really pretty, both in the code that composes them and their output in terms of errors and such. So I've spent a lot of time working on various kinds of parsing projects, lots of libraries to enable easier parsing. And my benchmark is generally how few lines of code does it take me to write a JSON parser. Untwine is the third iteration of these projects, and I'm going to talk a little bit about some of the previous projects as well. So, a bit of background on parsing. Parsing is easy. There's this approach that we use called recursive descent. For anyone unfamiliar, the basic idea is that you write a simple function to parse a simple piece of an input. So it'll only take a small chunk, and the rest will be left, and then you can have a simple parser for like a Boolean, for example. It'll parse true or false. You could have a simple parser for a number, and then you can take these functions and write other parsers that call those in order to do their parsing operations. And this approach, it'll trivially parse basically anything. The parsers that you write with it are generally fast. The code is simple. The code is readable, but it can be a little bit verbose. A JSON parser written this way, a handwritten one, is generally about 200 lines of code. So not bad. But parsing is also hard. We don't have the same kinds of expectations and requirements from our parsers that we once did. We no longer just want our parsers to be able to handle valid input. That's more of an edge case, to be honest, especially when we're talking about parsing a programming language syntax. We want meaningful errors that will point out and visually show you what went wrong and how to correct it. Not only that, we want errors that can, well, we want a parser that can take in an input that has multiple errors in it and can show you all of the errors at once. You don't want to get stuck in a loop where you're correcting one error, recompiling so that you can see the next error. If there's 10 things wrong in your code, you want to be able to run the compiler once, see 10 errors, and fix them all in one go. And on top of this, we want the parsers to be fast, and we want the parsers to not have super complicated code. So this is a pretty long list of difficult requirements for modern parsers to meet. And personally, I don't really want to write handwritten parsers that do all of these things because it's rather difficult. So I've made some previous attempts at parsing libraries. I'm going to touch on them just pretty briefly. Two of these libraries, Redlex and Flux, are basically the same idea. You would have this sort of BNF file, which describes the syntax that you're trying to parse. This is a description of JSON. You'll see it's very short and sweet. And from this, you'll get a parser that can take in valid JSON input and spit out an abstract syntax tree. Part of the problem with this approach which I can show you in the code here, is that you end up needing to specify a bunch of things. So it's not actually parsing all of the JSON into a format you would usually use. You need to still say, well, parse the integers into integers, parse the doubles into doubles, and all that stuff. And the type of every entry in this syntax tree is just token. So if something goes wrong, if you didn't get the input that you expected, it can be kind of difficult to debug that because you don't have any further type info. And we also need to set these rules, like remove any tokens that don't come from a named rule. If it's matching just a string literal, like a literal opening square bracket, for example, discard that token. All of these, if you get these rules wrong, this parser will break, and you will only find that out at compile time. So that's really not ideal. Um, and that'll just help also establish some of the additional goals of this project. The other approach that I tried was parser combinators, which is the idea is similar to recursive descent. You basically have simple functions. I don't know if you all can see my mouse cursor. Let me know if you can.
Yeah, we can see it.
Okay, perfect, because I want to use it to point stuff out. So you can use it to easily create simple parsers, and then you can combine them with these combinator functions that allow you to chain these operations together. And it's pretty simple. Here we are just defining a term for a basic expression parser. It can start with a negative sign followed by an expression, or it could be an expression wrapped in parentheses, or it could just be an int literal. So this is for a very simple expression parser. But you can see that that's a little bit clunky to read. It's not necessarily the most obvious. So untwine is really something in between these approaches. It is a formal grammar intermixed with the code to process that specific rule. It generates a parser without the downsides of these parser generators that I've made in the past, and it is even more compact. So those parsers would take about 60 lines of code in addition to the 14 or so lines of BNF. And I'm going to show you what the syntax looks like for untwine now. And then I'm going to show you what the JSON parser looks like. The syntax looks a little bit like regex. You have named rules. So you have a rule called word and you have a rule called word list. And you can see that you can use variables to capture individual values in this expression that you're parsing. And the parser here is just A to Z, so similar to a regex group, which would parse any lowercase alphabetic character. And the plus means any number of times one or more, so just like regex, but I had to change the syntax a little bit because it's within a Rust macro. And these angle braces here just mean that rather than capturing the actual output of this parser, which would be a list of characters, it's going to capture the substring that was parsed. So it's going to give you a string slice, and then we just convert that into an owned string. And down here, right, and since this is a function, we specify the return type, and this is just the body saying what the output of this parser is. Word list, since we're not even doing any kind of conversion on the values being parsed, we can just say this is equal to this, which has this return type. So it's just going to parse, this reads as a word list delimited by spaces. So this weird little $ syntax just means this is the delimiter for this which we are parsing. And the plus again means any number of times, but at least once. So we're parsing a list of words separated by spaces. And that'll give you a list of strings. So with this custom syntax, I can write a JSON parser, not counting this line up top or the closing curly brace or these settings up here. The actual parser logic is 12 lines of code. And it is a little bit cheeky what I've done here because I'm not counting some things. I basically just want to be able to give you a low number to flex. But it's also not technically a fully complete JSON parser. There are certain things that it won't handle. The main example being Unicode escapes. So if you do like \U and then a Unicode code point, you're just going to get a literal U and then those numbers in your string, because it just treats it as any escape sequence followed by that character just evaluates to whatever the actual character is. But you can see we just have 12 rules here. I have compressed them a lot more than I normally would, again, for the sake of being able to brag. But, 12 lines, and you can input JSON, and it will parse it successfully. So this is just the REPL, which you can spin up for any parser that you make with Untwine. The REPL is just a nice debug interface that comes with the library. So how does this actually work? It's Rust macro magic. When you write this custom syntax, it gets rewritten into parser combinators that the library comes with. And I will note, these are very different from the kinds of combinators you would likely use if you were actually writing this yourself, because it's all generated. And I think the best example of that is the fact that this JSON parser, which is 12 lines of code, expands to 2,400 lines. So definitely not something you would ever write yourself. And what do we get out of this? The most obvious thing we get is brevity. I mean, the code is very short. I've talked about that enough. But I'm going to spend the rest of this presentation talking about the other characteristics, which are, it's highly performant for what it is. You get good errors from it. You get error recovery from it, which is what I was talking about before, when you want to be able to recover multiple errors from a single input. And it has IDE integration. And what I mean by IDE integration is that you don't lose the ability to have LSP or something give you this feedback, even within this custom syntax. That's just thanks to how Rust handles macros. But you can see I have this rule list, which is just an opening square bracket, white space, and then it's parsing a list of JSON values separated by commas, white space, and then a closing square bracket. So that's the syntactic definition of a JSON list, and we're capturing it to this values variable. And if we hover over this, you'll see that the IDE can actually tell us this is a list of JSON values. It can tell us the type information even within this custom syntax. And I think that's a major benefit of using this approach. Because if you also want to rename things, if you want to refactor this, it becomes much easier because you don't have to manually go through and find every instance. You can use all of the IDE actions you're used to manipulate this code. So I want to talk a bit about the errors, or rather show you the errors that Untwine can generate. One is a blank input. If you don't give it anything, you will get this error saying, I expected you to give me a JSON value. It's showing you the line number. It has a caret pointing out the position in the input. And you get this error message saying, line 1, position 1, expected JSON value. This really just sort of shows off the format that it uses. It's very much inspired by Rust's errors. And if you give it a partial word, like if you start typing true and you don't complete it, it can actually highlight what specific part of the input it's referring to. So it doesn't only point out an individual character, it can highlight pieces of the input. And if you have an error spanning multiple lines, it can say, it started here on line 1, and then you forgot to close this list on line 4. And, there's more stuff in the middle. So these are, I like to think, very, very nice errors that give the user good feedback. And we haven't given it any more info than just describing that syntax using the format of Untwine. And additionally, error recovery. Here we have one very short input that is fraught with errors. It'll tell us, you forgot to close your list. It'll tell us you forgot to complete this Boolean, And it'll tell us, because you put a comma, we are expecting another JSON value there. So it can really give you lots of errors, even with a complicated input that's broken in many ways. So how does that work? Um, and this, I'm going to glaze over a lot of the finer details here, but the basic approach is there are a lot of errors that will be generated in a successful parsing input that we don't care about. For example, white space will often fail, but we don't care if it fails because it's optional in basically every case. Or if we are parsing several choices, so for example, a JSON value could be an integer or float or a boolean or null or a list, etc. Many of those will fail before one of them succeeds. So in general, the rule is just keep whichever error is the deepest or was encountered the farthest into the input. For being able to report the range of an error, all we really do for that is we have, whenever you have a named rule like list, it's going to hold on to the position that it started parsing at. And then if an error happens, it can stay where that started. That's all it really is. But recovery is where it gets a little bit more complicated. But there's only really two rules at play here, two cases that Untwine will automatically handle for you. One of those is for if you are parsing a delimited list, it will, if any element fails to parse, like if you're parsing a list, it will recover to the next delimiter. So if it fails to parse an element for a JSON list, it'll recover to a comma. And for wrapped rules, again, like a list starts and ends with square brackets, if the inner values fail to parse, it will recover to the closing delimiter. So for a list, it would recover to a closing square bracket. And that just means it'll store the error away in some list of errors, and it will try to continue parsing as if nothing happened. And you can still get a partially complete input, which has error nodes out of this. So what makes it fast? And before we get to that, how fast is it? The benchmark that I used for this was a 5 megabyte JSON file. I benchmarked my previous libraries with this as well. And it's the same file for all of them. Redlex, written in Java, took 570 milliseconds to parse that JSON input. Flux took 260 milliseconds, quarter of a second. Untwine, when I first wrote it, took 150 milliseconds, and I was able to optimize it with 3 optimizations down to 60 milliseconds, whereas a handwritten parser can do it in 35 milliseconds. So Untwine is about half as fast as a handwritten parser. And what can we learn from these optimizations? What do they tell us about a CPU and about optimization in general? So the first optimization is very, very simple, to the point where it kind of baffled me for a little bit when I first tried it. So this here is the type that I was using to represent the output of a parser. It can contain an optional success value, and it can contain an optional error value. Normally, the errors that Rust gives you can only hold one or the other. But there are cases where we have a successful parsing operation and we still want to report that an error happened. Um, and in order to be able to point out where that error was, we want to store the position of that error. The only change that I made to take this down from 150 to 100 milliseconds, so a 1/3 reduction in runtime, is I made the position stored unconditionally. And this doesn't really make sense at first, but if you think about it, every time a parser is spitting out one of these, you want to check, we're keeping the deepest error. So you want to check, did it have a deeper error than the last thing we parsed? And in order to do that, you have to check, is this error actually present? Yes. Is the other error actually present? Yes. Then we compare the position and take whichever one is greater. By storing the position unconditionally, we only have to make a single check as opposed to those 3. we can just say isn't greater. If so, take the error. Even if it's nothing, we don't really care. Because if a parsing operation succeeds deeper than the deepest error, then we know that that error didn't prevent it from parsing completely. So the reason this made such a big impact is because it reduced branching. Branching is by far the most or I shouldn't say the most, but it's one of the things that will really hinder performance, because modern CPUs will try to speculatively execute your code ahead of what the values are even known for, and it will do this by trying to predict the outcome of certain branches. If you reduce the number of branches, it reduces the chance that that branch prediction fails, and that means that you save the CPU a lot of effort. Because when a branch prediction fails, it has to roll back everything to the state where it was before it speculatively executed the code that it thought was going to run. The second optimization I made is the most complicated one, or at least was the most complicated to implement. It's fairly simple to understand conceptually. It took us down from 100 to 75 milliseconds, so around a quarter reduction in runtime, and it takes advantage of things that only a macro could really do by having compile time insight into the structure that you give it. And it's just another way to cut branches. So I'm going to go back to the JSON parser that I showed you before, just to give this as a quick example. What this optimization does is it optimizes cases like this, where you have this is equal to a boolean or null or string or float, etc. The issue with this sort of setup is that normally you are going through one by one and trying to parse, is this a boolean? No. Is it null? No. Is it a string? No. Blah, blah, blah. It's a list. So we're going to parse it as a list. But we did all of this work checking these conditions that are just false. So with a handwritten parser, you would usually do this by looking ahead and knowing what kinds of values can come based on a given character. And that's exactly what Untwine is doing here too. It's seeing that Boolean can only start with a T or an F. Null can only start with N. String can only start with a literal quote. A float can start with a digit or a negative sign, and so on. And what this optimization will do is at compile time, when you have a choice like this, it will generate a match statement that will look ahead by one character and use that to identify which rules can actually be parsed from that. And that turns out to make a pretty big difference because you're just cutting out a lot of work that doesn't need to be done. And let me get back to that slide. So there are limitations to this optimization. One is that you can't always tell perfectly which characters correspond to which rules. You might have some overlap sometimes, in which case you might need to check multiple things. And if a rule starts with a character that could be nothing, so if it starts with optional white space, for example, then it becomes a lot more unclear. And usually what ends up happening is it'll have to run through all of the choices anyways. But it's a situation where most of the time you can cut a lot of work. And even if this optimization doesn't help, it'll never hurt anything. The third optimization I made was a simple one that would often be regarded as kind of bad practice, which is having a single global location, or global in quotes, because it's really storing the error inside this parser context value. And you can see that that's the only difference in these signatures. This is the signature of a function that parses some value t. And the only difference is that we're no longer returning any error. We are only returning optionally the success value. And that means we're marking whatever errors happened in this context object in a single variable, which is here. We are storing it in an unsafe cell, which again, kind of bad practice. And we are storing the position of that error. Now, this optimization was the smallest. It was about a 20% reduction in runtime, down from 75 to 60 milliseconds. And it's just shoving it all in here, all the errors. The main reason that this makes a difference is that we are passing around less values, or rather smaller values, on the stack. When you use this parser result, even if you're not returning this error, it still has to allocate the amount of space that error would take, which means you are now returning a larger result, even if the parsing succeeded. And by eliminating that, and by passing around smaller values, we just do less work overall. Additionally, by storing everything in one place, rather than having a bunch of different errors that are generated and then returned from different locations, we can improve the cache locality, meaning that the error can just get cached in one place, and the CPU doesn't have to go looking for anything. So, sorry, I need a quick drink of water. But what this tells us is that sometimes it is worthwhile to sacrifice best practices in order to get better performance. I think in this case it makes a lot of sense because parsing is kind of a fixed problem set where you have a series of basic operations that you combine in order to do all of your parsing. And that's why I was able to make a compact syntax for it in the first place. So I think this is a good use case where it makes a lot of sense to take the performance over best practice. So next, I briefly want to talk about an expression parser I made with this. And this is kind of hinting at my larger goals with this, which I'll get to in a second. So with this parser, all I really do is I define a single function to operate on two values. So you see it takes the operands and then the operator, and it's just going to evaluate them just like that, very easy. And down here, this is the entire expression parser, and it is capable of handling order of operations, as you can see, and parenthesized expressions. And I don't use the shunting yard algorithm or anything. The only trick that I have to do for this is say an addition is composed of multiplications, where a multiplication could just be a single term without any operation at all. And you could do this up and up to apply to other operator precedences. So it really cuts out a lot of the difficulty of making an expression parser. And if you have an expression parser, you're kind of like halfway to a programming language. And that is my goal. I love building programming languages, and I want to make it easier. This is just the first piece in a toolkit I'm trying to make. And the other two pieces that I'm aiming to build right now are Hingepin, which would be a type inference library, and then I'm going to make a bytecode interpreter library. But my goal with Untwine is really, I want to be able to mess with syntax and iterate on it very, very quickly without a lot of risk. And Untwine makes it very easy to do that and to still get good parsers out of it. And that's about all I have for you today. I'll open it up to questions now.
Soon, that was awesome. Thank you so much.
Yeah,
I'll
thank
start
you.
us out and then maybe people can jump in. So maybe just to get started, like something that Jacob and I are both very interested in is this idea of parser security. And I wonder, as a real parser aficionado, if you've thought a little bit about what might be doable within Rust to use the type guarantees you get from Rust to be able to like essentially prove interesting things about parsers and how they'll handle malformed inputs as
Mm.
they get compiled. Is that something you've thought about at all?
I haven't put a lot of thought into it in particular, but I think that most of the vulnerabilities in a parser would likely come from like buffer overflows, right? And I think it's mostly a lot of things that Rust kind of protects you from automatically. And I think so one thing that is cool about Untwine is that you are basically using a formal grammar here. And one of my ideas that I haven't implemented yet, but I'm still thinking about, is an additional setting which would be a file location to then spit out just the formal grammar, which you could
Oh,
use
interesting.
to perform all sorts of analysis on it. One caveat to that is that this does support context-sensitive parsing. So a big limitation of BNF is that you can't really specify something like Python syntax, where
Right.
you might have a number of indentations characters that is based on something contextual, like how many layers deep you are in code bodies already. So it would definitely get tricky if you have a context sensitive parser that you're writing. Um, Untwine supports that by just allowing you to pass arbitrary context objects to your parser. But yeah, it's it's something that you might want to check the formal grammar. Although I'm not sure how much that could really tell you about security, since I think most of the issues with parsers come from memory issues. You could correct me if I'm wrong on that.
Yeah, that sounds reasonable to me. Jacob can maybe speak to it a little bit better than I can. There's one other
Okay.
aspect I would say, which is um, kind of weird machines, like the idea that your parser, in some sense, um, maybe you don't intend to parse a programming language, you intend to parse like an image or a JSON file, but your parser is more powerful than you expect it to be. Like there's this very
Hmm.
famous article in the journal POC or GTFO where somebody embeds a Nintendo emulator inside a PDF, and it
Yeah,
turns
yeah,
out,
I've seen that.
PDF is sufficient for that, right? So that's but that's complicated. Like it's much easier to prove the positive than the negative. I have no idea how you would go about proving that a language is not Turing complete. That seems very,
Right.
very difficult to me.
I mean, I think that arises much more when you're parsing a byte format, and that's really
Mm,
not what Untwine is for. One of its limitations is that it takes in a string slice, a Rust string slice, which has to be valid UTF-8, and that kind of negates the point of byte parsers in the first place, because they're usually not going to be valid UTF-8.
gotcha.
So sorry, I don't have my camera on. I'm feeling sick today, but I'm just going to paste a
Oh,
link
good.
in the chat that's about what Max was talking about. There's a DARPA project that was all about secure parsers and different things that might be of interest if you're curious about reading it later.
Oh
And
yeah,
Gina,
sure.
I missed the start of this talk, so I'm sorry if this is something you went over, but I'm curious, how did you get started going down this rabbit hole? I know you talked about liking developing programming languages and wanting to
Yeah.
make that easier, but presumably it started from somewhere. There's got to be some story here, right?
One of my first projects on GitHub is a really crappy JSON parser that I wrote in Java like 8 or 9 years ago. Um, it's I think like 50 lines of code. It mostly uses regex to try and extract values. It's horrible. Um, but I couldn't tell you why I'm so fascinated with string manipulation. It's just something that's really captivated me. And as I've grown as a developer and started learning other languages, I've just kept wanting to find ways to make it really easy. Because I guess I'm really partial to like DSLs and such, and I just love being able to write custom languages to solve very specific problems. For example, I made a command library that has a custom command format. So you write a file in that format and it'll parse it to get all of the metadata about your command and then hook into methods in your code. So that's just an example of the things I like to do. I also wrote a lot of expression parsers when I was younger, made like a crappy graphing calculator. I mean, the short of it is I like reinventing the wheel. And if you reinvent the wheel enough times, it might start being decent enough to replace a normal wheel.
That's cool. I love that. Thank you for sharing.
Yeah.
Can you use Untwine to build things that are not exactly parsers? Like I'm working right now on an inliner for Python, but I have a project where I need to be able to turn a large, piece of Python code that has many different files, import one another into one one Python script. And so that's sort of like parsing, but it's not exactly parsing, right? Are there other applications, maybe not inlining, but other
Well,
applications beyond parsing that you think are
I mean, it sounds like parsing would be at least a part of that, right?
yeah, to some extent, yeah.
Yeah, so you could probably use it for that.
Okay.
Because it can handle context-sensitive parsing, and Python's context-sensitive.
Yeah.
BNF couldn't handle it, but Untwine should be able to. I think it really is just for parsers. I'm not sure what else you would really do with it because all it does is parsing. But there's lots of different applications for parsing, yeah.
Yeah, makes sense. What sort of problems do you want to solve with the languages that you're working on building?
That's a little bit tricky to answer because it'll vary a lot. I made one already called Fender that was kind of meant to be a bit like awk, where it was a string manipulation language you would use on the command line. Didn't really play out the way that I wanted it to, but it was a group project and we all kind of just had different ideas about what it should be. Right now, I'm working on, or I guess more theorizing, a language called Elude, which lets you just use type inference for absolutely everything. And I guess it would be most similar to like Java because it would be a bytecode interpreted language that you compile into bytecode ahead of time, and then you would run on the interpreter. I really just want to fix some of the issues that I had with Java. A lot of goals similar to Rust too, but trying to reduce the developer burden of having to think about memory management and a lot of the specifics of like typing and the borrow checker. Um,
That makes
yeah,
sense.
I really love like powerful type systems, and I think that's why I chose Rust as well. It's one of the many reasons I chose Rust as my go-to language now.
Yeah, I've been thinking about the ownership system recently because I think I believe two things simultaneous. I'd be curious to know if you disagree. One is that you do ultimately save time by using it compared to the time you spend debugging your broken C code. And
Yeah,
like it, right, when you write code in Rust. And two is that it's a little bit like, I don't know, like brushing your teeth or something. Like it's like not pleasant, right? Like you spend a lot of time thinking hard and not being able to just kind of listen to a podcast and cruise. Like you need to actually engage with your code and understand what you're doing in order to
yeah,
to write your code properly. Um, and I don't have any brilliant ideas for this, but I've been wondering whether there's like some way it could be made much easier, like maybe a graphical system that has some graphical language for reasoning about ownership that makes it easier for like normal software engineers to reason through, where you're kind of drawing like flow diagrams or something. I'm not quite sure, but I feel like there's got to be a better
yeah,
way to communicate ownership to the average software engineer so that they don't have this like onboarding process with Rust that's basically, okay, I'm going to spend like 2 months wrapping my head around this thing and making it intuitive,
right.
and that before I'm like any good at it, right?
Well, I think most of the difficulty there arises because Rust wants to be explicit about absolutely everything. Um, I've seen, God, I wish I could remember what it was called now, but I did see an example of a similar idea someone had tried where ownership is basically implicit, where you don't need to pass references, or you, when you use references, you don't need to specify lifetimes on everything because it'll just sort of assume that lifetimes are valid, and then when you actually use them, it will create these regions that, kind of
Oh,
like arena
interesting.
allocation, will um deallocate everything at once when some value goes out of scope. Uh, but in general, I think there's a lot that could be done to make Rust do more for you implicitly, but I think the risk that you run with that is always that you're gonna compromise the developer's understanding. And personally, I think that if you're trying to make a large project and you need it to be really reliable, I think it's definitely better to be explicit about everything, because you learn more that way and you can be more sure about your code.
Yeah.
So when
Yeah,
you
I
first
agree.
start writing Rust, it's very complicated and difficult, but you get used to the borrow checker. And I don't find myself pulling my hair out nearly as much as I used to over it. So it's just like switching from a dynamically typed language to a statically typed one. It's going to be a learning curve. But I think it's just something that could be taught better.
Johnny, you just put something in the chat. Do you want to tell us what it is? If you don't have audio, no worries. June, maybe another question. So does your adventures as a parser extraordinaire, does it have any applications for your, work at kind of the intersection of like AI and software development tools, or is this entirely kind of a philosophical
On
exercise for you?
my tab just crashed, so I don't know what the last thing you heard me say was.
Oh, I'm sorry. I think we didn't hear you say anything when you lost your screen sharing.
Okay. Did you hear my answer to the last question?
Yeah.
Okay. So I guess it just crashed on its own then. Were there
Okay.
any more questions?
I was just going to ask if your kind of exercises as a parser extraordinaire have had implications in your professional life, or if these are purely academic and personal,
Mm.
which obviously there's no negative to that. I'm just more curious, like, have you as an actual software engineer working on kind of cutting edge AI stuff encountered in your day-to-day life a situation where you're like, oh boy, it's actually kind of awesome that I'm really good at parsing because this came really in handy for this particular task or something?
I have kind of had to break it out in a few cases. There have been a few cases where it was really handy for me to whip up a quick macro in Rust, of the procedural kind, so the kind that feels more like black magic. And so we have a question in chat too. Oh, that's just a comment. But yeah, I would say more so than parsing in particular, my inclination for reinventing the wheel has led to me very, very deeply understanding the basic mechanics of things that a lot of people kind of gloss over, and they see it as just like, an engineer, someone who hooks things together that are already made. Um, so I think I definitely gained a very good understanding of like data flow and just program structures in general and how to approach problem solving from the ground up. And I definitely think that that has made me a better programmer, and I don't think I would be the programmer I am today if I hadn't learned that way to begin with, of just
Yeah, that makes
constantly
sense.
reinventing things that didn't need to be reinvented.
The calculator example is an interesting one because when you I mean, that's an exercise a lot of us have done, right? And like when you
Yeah,
do that, you learn reverse Polish notation, and RPN is like the intrinsic representation, right? In the sense that you have an operator and you have two operands, like you have
yeah,
plus and 5 and 3 or something. And um, I knew RPN as a kid because my dad really likes RPN calculators and has like, an old RPN calculator. Chris is giving thumbs up because he likes RPN calculators too. And there are competitions that show that like in competitive finance, which is a thing, people are significantly faster using reverse Polish notation calculators than they are using standard calculators because they don't
yeah,
need to use parentheses, right? So you
yeah. That makes
save
sense.
one button press on every level of your syntax tree. Since you don't have a start and end parentheses, you just have an enter. And so it's a great example of how there's like, if you, there's a most compressed format, and then there's like less compressed formats that people use on paper, but the most compressed format is the
Mhm.
syntax tree of RPN, right? And so that's a place of what you're talking about where like building the parser makes you understand the problem at a more philosophical level. You understand like philosophically, like what do the symbols actually add up to? What is the intersection between the syntax and the
I
semantics
think
here?
there's also a lot to be said about the understandability of things, because like with reverse Polish notation, you can often have a lot of nested operations, and it gets to the point where it's very difficult to reason about. Because you'll have like 4 operators, and you're like,
Right.
where are the terms? What are we operating on?
Yeah,
And
totally.
it can be hard to visually parse out where anything starts and ends. And I think there's definitely something to be said about using a completely custom syntax for this as well, where, you know, it's very, very compact. And one of my concerns was, is this going to be unreadable? And I think you always just have to strike a balance between readability and expressivity. And I think I did that pretty well with Untwine. I definitely compromised it when I shoved everything onto like one line functions, um, with my examples. But as it would normally be written, I think it's a fair compromise.
Learning
this is
Lisp. Go for it.
This is a totally off the wall question, but in talking about the deep dives and really understanding things thoroughly, I've often found, like when I was figuring out what I wanted to do for work, that everyone was like, "Oh, you should go work for Fang, like get a job at one of these fancy like big tech companies." And I've often like had some distaste because I feel like it's not actually getting to the core of the things a lot of the time. And one other community where I've seen this type of ethos and way of thinking be really prevalent is in the security community, like vulnerability researchers, people who do program binary analysis and reverse engineering and types of things. Is this something that you've dabbled with at all, June? I wonder if you'd like
No,
it.
I really
Or
haven't
thought
done
about
much by
it
way of
before.
security and reverse engineering. It's just not really my field of interest, I guess.
Okay.
But it is really, really cool. And I could definitely see how, when you're working at a much higher, more abstract level, it's very easy to miss a little detail that could compromise security. So it makes a lot of sense that people in security would be focusing on working at the lowest level possible, rather than glazing things over, as engineers often want to do.
Cool.
Jacob, could you maybe tell June about ROP compilers, because I think that they would get a kick out of that.
Oh yeah. Yes, that's an interesting one. So sorry, I'm just trying to think about how to explain this. So yeah, so okay, I'm trying to tie this back to some of the stuff we were talking about here. But basically, what happens is, let's just pretend that you're in some system that's a compiled language, like C or something, and you're working on assembly instructions. So it's not bytecode, it's not interpreted. And one thing that can happen is if you find a buffer overflow or any type of vulnerability that gives you execution, you can just imagine you get to point the instruction pointer at anywhere in the code base. So one thing you can do is you might be able to say, oh, perfect, I want to jump to this specific function that gives me a capability that I want. But another thing you can do is say, these instructions are all blank bytes long. If it's a RISC like ARM, they're all fixed alignment, but if it's x86, they can be variable. But anyway, if you jump at a weird offset that's not at the start of an instruction, you can find all these kind of hidden instructions that were never part of the program to begin with. Like if you are 1 byte misaligned from a move, now it might be this crazy thing that just depends on whatever the registers were that were being moved. There's a bit more to explain, but just setting the stage that way makes sense for people. Do folks sort of understand what I'm talking about
Yeah.
so far? Okay. So then what you can then do here is say, perfect, I have all these different instructions that I can try to chain together. And if I specifically search for ones that end in jumps, they do some small modification to the program, like clear register, add something, whatever it is, and then you jump somewhere else. You can, with this one initial instruction pointer arbitrary set, you can then chain all these things together. And there are often these totally hidden kind of embedded programs where you might have this. I'll try to find a link to share after I finish explaining, but you might have like, here is a Pokemon game that you exploit, and then someone finds this wrap compiler inside of it that plays Pong or something like that, where you can do this weird work of embedding programs that aren't necessarily there.
I have seen someone do that with Mario, I think it was.
Yes, that's exactly the one I was thinking of. I'll find a link for that. But Max, I'm in trouble like tying this back to the JSON
Well,
parser. Was I missing something?
I guess the point is that it's sort of a fascinating problem around parsing and compiling. And June, not being a security person, might not be aware that there is a whole world of parser and compiler engineers specifically focused on, problems like this in security, right? So
Oh,
I
I'm
guess
sure,
like
yeah.
from my eyes, there's kind of two problems that get studied a lot from serious security folks here. One is how to compile into a meta language. So you find some like language of gadgets, of ROP gadgets, and then you build a compiler where you can write straight up code in like C or Python or something and compile it into those gadgets. And then the other problem is almost the converse, which is here is a compiler. I want to figure out what the bugs are in the first place so I can compile that list of gadgets. Would you say that's more or less correct, Jacob?
Yeah, sorry for missing in a second. No, I totally agree. I think it's a really fascinating blend, and I love this idea that you have these more powerful machines that can then have kind of hidden programs in there, these weird machines and stuff too. No, it is definitely interesting. I'm gonna try to find
Anyway,
the link.
we'll rope Jacob into giving a talk about this in the future because they're doing a
Yeah,
PhD
I'd love to hear it.
at Dartmouth
that'd be
just
awesome.
Really
about this.
fascinating.
Yeah. Cool. Well, any last questions before we call it? And I don't want to
It
just
looks like
ask.
Chris might have had one.
Oh yeah, Chris, do you have a question?
No?
Nope.
Okay.
Okay. June, this is super cool. Thank you so much for taking the time to talk to us on a Saturday.
Yeah, thank you for letting me host it.
This was a lot of fun, and yeah, look forward to seeing you at future events. Let's do a security one with Jacob once they've had some time to settle into the PhD, and you can come and ask good engineering questions about the security stuff. We'll flip the roles.
Yes,
All right.
please. That sounds great. And one last note is I added a YouTube link where it's not Pong, but it is someone using some vulnerability in Mario to play Snake somehow. And this is with
Oh,
Rock.
cool.
So there isn't actually any Snake game written into Mario itself. But if you get arbitrary code execution, they can find a whole bunch of these little functions that were never
Nice.
supposed to be there that they chain together and can play something totally different. So
I'll put a link to that next
Yeah, I'll
to
check
your
that
talk
out.
on the website so people can find it.
yeah.
All right.
All right. Thanks,
Well,
June.
Okay.
thank you everyone
Thank you,
for
everyone.
attending.
Adios.
Thank you.